Okay, this should be a pretty quick video, and as a side note, I have gotten a new mic that I think will be more reliable than my old one. I'm not sure how the sound quality will compare, but I think it won't cut out like the other one had. So y'all let me know what you think. This video is going to be over calculating work. It should be pretty short and sweet. We've kind of talked about all the conceptual stuff, and so now I'm just doing a couple examples so you can see how to actually calculate it. So all we're going to do here is a quick equation review, and then we'll do some examples. So the goal is short and sweet. It's to calculate work done by a single force. That's one of the level 2 items on your proficiency scale. So we need to talk about how to do it. So quick equation review here. Reminder that work is equal to force times distance. And the really key part here is this F parallel bit. Right? So what's really important is that I'm looking at the parallel component of the force only. I don't want the entire force. I just want the parallel component. So as a little review, we kind of looked at this before where it's like, well, let's imagine that my displacement is somewhere over here. So there's a vector representing my displacement. And my force is maybe here. Right? So there's my force. Put a little vector hat on each of those. And the idea would be that I would know some angle between the two of them, and I don't want the entire force. What I really want is I just want the parallel component of the force, F parallel. And we could draw in here that there's also going to be a perpendicular component, which we call F perpendicular. And the idea is that, this one's not doing any work. Only that one is. And so if I walk you through the trig, which I'm not going to do again, but if I were to, you would end up seeing that you get this part here, the F cosine of theta. That's where that comes from. So when we're looking at this second equation, the second representation that you may see, it's basically just saying that F parallel could be F cosine of theta. But you have to remember that's using theta as this angle measured between the displacement and the force. So the first example that we're going to do is a pretty straightforward one. A box is pulled across the surface by a 250 Newton force applied at an angle of 32 degrees above the horizontal. So if I just do a quick doodle to help orient myself on the problem, I've got a displacement here, and this is basically what I was talking about up there. So I've got a displacement and I've got some sort of force. Here's a box, right? There's a box that's being pulled. And I know this angle between them, right? That's this 32 degrees. So this is really just applying the equation. Very straightforward. So the equation is that work is equal to FD cosine of theta. And all you have to be careful about is that you know this angle, or that you use the correct angle, and it's always the angle between these two things. So that should be fairly easy to remember. And so I'm just gonna plug numbers in. So the force is 250 newtons times the distance, which it didn't give you because of course I didn't. Let's just say, for the sake of the example, then that it's pulled 12 meters across a surface. So times 12 times the cosine of, and my angle here is 32 degrees. So then I can take that and put it into a calculator. Give me 1 minute to do that. So let's see, it's 250 times 12 times the cosine of 32. I make sure I'm in degree mode here. And I get that the amount of work that's done is 25. Well, I only get 2 sig figs, so let's call it 2,500 joules of work. So there's my answer, 2,500 joules. So it's really fairly simple equation to use. Let's look at one more quick one here. This one I actually did give you the distance that it was moved. So I've got a 2.7 kilogram ball is thrown upward and reaches a max height of 1.4 meters. And I want to know how much work is done by gravity. And so if I focus just on gravity, I've got a ball. It's quite a heavy ball. Probably should have thought through the numbers a little better, but there's a ball. and the force of gravity on that ball is down, and my displacement is up. Now, what's important about this example is well, there's kind of two things. The first thing is that those are exactly what we would call anti-parallel. So maybe I'll define that word real quick. Anti-parallel, which means in the same line, but the opposite direction. So it's something that you really only use when you're looking at things like vectors, because they're clearly moving, that way and that way, but they're going the opposite ways. So that's anti-parallel. So when I use my equation, it would be more appropriate for me to think about using this one, that that work is equal to F parallel D. And now I would know that the angle between those two, like it is parallel, it's anti-parallel, and that would just tell me that this thing is going to be doing negative work, so it's in the opposite direction. So the math here should be pretty easy. First, I actually have to calculate my force this time, right? So I have to calculate the force of gravity. Important to recall that the force of gravity is equal to mass times gravity, and so maybe I'll just rewrite that with that in there, FGD. That looks kind of familiar. Interesting. And then I'm going to plug in my numbers. So it's 2.7, it's the mass, times 9.8 is gravity, times 1.4 meters is the distance. And once again, I'm going to put that in my calculator. 2.7 times 9.8 times 1.4, and I get 37 joules. 37 joules of work. So there's the work that's done there. Now you may have noticed that this is dangerously close to our gravitational potential energy equation. And that's actually because if we were doing this in like a really formal physics class, that's actually how we would derive the equation for gravitational potential energy. And there's an interesting result from that. It's that, and this is not the point of the video, so don't stress about this, but there's actually an idea that work for conservative force is equal to the opposite of the change in potential energy. And that reminds me, I missed a point I was trying to make here. What is that? This is negative work that's done because they're opposite directions. So negative work that's done here. Now, another thing I wanted to point out is that you could still use the other equation. So I want to show you that real quick here. If I wanted to use work is equal to FD cosine of theta, you can do that, and that's perfectly fine. Just be careful about this angle. So if I plug this in, it should be 2.7, again, times 9.8, because I'm looking at the times the mg, times 1.4 times the cosine of. Now, what angle do I put in there? Well, they're exactly opposite of each other. And so what we should put in there is 180. And if I put in 180, some of you guys may know from pre-cal that the cosine of 180 is -1. And so what we end up with is that whereas over here I have to think about and maybe forget, as I did, I have to think about what sine the energy should be. If I use this and I put in the appropriate angle, it'll actually do the sine of the energy for me, right? Because it's 180 degrees, and that is going to give me a negative value. So if you put that into your calculator without doing anything else, it will spit out negative 37 joules. And so there's just kind of a little alternative way that you can think about it. So this video, very, very short and sweet, just looking at adding on a couple of quick examples of how to use the equation. It's a pretty straightforward equation, but I want to make sure you had a resource in case you had any questions or wanted to see how it's done. So very quick little recap here. So we have two representations of the equation, right? F parallel D and FD cosine theta. Those are equivalent. This one just breaks down that F parallel bit into F cosine of theta, where we know that the angle theta is measuring between the displacement and the force. And so in cases like this, you definitely have to use the second version. In cases like this one, you could go either way. Because it's anti-parallel, I could use the F parallel D, and then I just have to make sure that I'm careful about saying, yeah, that should be a negative. If I use this equation and I put in the right angle, it actually will do the negative for me. And so both equations actually work perfectly fine. Then there was this extra bit here that really isn't important for today's video, but we can see that, and we're going to come back to that in a future lesson.